This video is the last one in the series, like a corollary to a big theory. To properly understand the corollary, you simply have to know the theorem. So make sure that you have watched my video about the geometry of expected values, as I will rely on it here. But to recap, in the last video we have seen that if the sample space only contains a finite number of elements, say n, we can represent random variables as n-dimensional vectors, and if we then use a probability-weighted Euclidean scalar product on this vector space, the expected value can be seen as an orthogonal projection onto the subspace of constant functions. So in today's video, we will use this geometric perspective to better understand the covariance and with it the very related notions of variance, standard deviation, and correlation. Intuitively, the variance and the standard deviation are a measure for the variation of a random variable, and the covariance and correlation describe how two random variables vary together. And since the variation of a random variable basically captures how non-constant that random variable is, the thing we're interested in is the difference of a random variable compared to its projection onto the subspace of constant functions. That is, the difference to its mean. And I will often call this quantity the corresponding residual, which will somehow be the main character of this video. So I will actually start with the variance, as it is the easiest to set the scene. For this, let's recap the definition of the variance of a random variable x. It is the expected value of the square of x minus the expected value of x, so the squared residual. And if we write that out in our two-dimensional example, we find that in this probability-weighted geometry, this is simply the sum of the squared distance between x of omega 1 and the expected value of omega 1 plus the squared distance between x of omega 2 and the expected value of omega 2. So if we draw them into our plot, we get these two distances such that the corresponding squared distances can be visualized as these squares. If we now apply the Pythagorean theorem to this triangle, we see that the variance is simply the squared norm of the residual in this probability-weighted geometry. While this is already quite nice, you might be wondering why I am showing this Pythagorean theorem here, because in this setting it is actually kind of trivial, right? As it only needs the orthogonality of the coordinate axis and therefore does not really rely on the probability-weighted geometry. Although this is true, here's the catch. Due to the orthogonal projection, we can actually draw another right-angled triangle in this plot that includes the variance, namely the one where we connect the random variable x and its expected value with each other and the origin. So what are the side lengths of this triangle? Obviously, they are given by the probability-weighted norm of x, the probability-weighted norm of the expected value of x, and as we've already found out, the norm of the distance between them. So if we apply the Pythagorean theorem to this triangle, we find that we can rewrite the variance as the squared norm of x minus the squared norm of the expected value of x. And if we translate these geometric terms back into stochastic ones, we find the well-known formula for the variance as the expected value of x squared minus the square of the expected value of x. So that's pretty nice, because it means that the usual way of rewriting the variance can simply be explained geometrically in terms of the Pythagorean theorem, just in the probability-weighted geometry. Okay, so now that we've clarified that the variance is the squared norm of the residual of x, it's pretty obvious what the standard deviation is geometrically. Since the standard deviation is the square root of the variance, we get directly that the standard deviation of a random variable is nothing else than the probability-weighted norm of the residual of x. And that fits very well with the intuitive description of standard deviation as a measure for how far a random variable deviates from its mean, right? Now, before we go on, I want to make one important disclaimer, because I guess otherwise this might lead to some confusion. Do not try to read off these values from the rectangles of the coordinate system. because these rectangles show you the distorted Euclidean geometry. That is, how the Euclidean geometry is distorted to get to the probability-weighted geometry, which you can see from the fact that these are rectangles and not squares. So if you use them for counting, you would actually be counting in the Euclidean geometry, which gives you the wrong result. Okay, so let's go to the covariance. We've seen that the variance is the squared norm of the residual of x, and we know that this norm is defined in terms of a scalar product. However, as you probably know, the variance can also be written as the covariance of x with itself. So a comparison of these two formulas suggests that the covariance of two random variables x and y should be something like the probability-weighted scalar product between the residual of x and the residual of y. And in fact, if you write out the formulas here, you will find this to be true. So as we will see soon, the covariance basically measures the length of the residuals and weighs this by the corresponding angle between them. Okay, so let's try to visualize this by looking at two such residuals. With again our two random variables, x and y, project them onto the subspace of constant functions and draw their residuals. And what we get are residuals that are always parallel. No matter where we draw such a residual, they always point into the same direction. So that seems to be a problem, right? What we are observing here is actually not a mistake, but it is based on the dimensionality of the visualization. 2 dimensions are simply not enough. Because in this example, our space L2 is a 2-dimensional vector space, and the space of constant functions is a closed linear subspace of dimension 1. So we can actually write L2 as the direct sum of the subspace of constant functions and its orthogonal complement. However, since the overall dimension is 2 and the dimension of the subspace of constant functions is already 1, we simply get that the orthogonal complement also has to have dimension 1. And that means that all residuals are spanned by the same vector, such that there is simply no angle between them. To see this visually, let's figure out how this orthogonal complement looks like. By definition, it's all random variables such that the probability-weighted scalar product with the vector 1, 1 is 0, as this vector spans the subspace of constant functions. And if we rewrite this condition in terms of the expected value, we find that the orthogonal complement consists of all random variables with mean 0. So it's all random variables that the orthogonal projection maps onto 0, which is this gray line here. What I really like about this representation is that it gives you a kind of signal plus noise decomposition of random variables, because it tells you that we can write each random variable as the sum of an element from the subspace of constant functions, the expected value, plus an element from the orthogonal complement, that is a term that captures the deviation from the mean. Formula-wise, this seems kind of trivial, but I think from a geometric perspective, it is kind of beautiful. Okay, so the takeaway is that if we want to see the covariance visually, we need to make sure that the residuals are not one-dimensional objects, but at least two-dimensional. So we need to look at a three-dimensional example. And that means that our sample space now consists of values omega 1 to omega 3, such that our random variables can take up to 3 different values, which are attained with probabilities p1 up to p3. So as before, we need to scale the corresponding axis of the Euclidean geometry by the square root of the probabilities to find the probability-weighted Euclidean geometry. And as before, the subspace of constant functions is still represented by the diagonal and is still of dimension 1. Similarly, if we have some random variables, we can represent them as points in the space, just that they are now three-dimensional objects instead of two-dimensional. And by projecting them onto the subspace of constant functions, we still get the corresponding expected values. Okay, now, while the residuals are still orthogonal to the diagonal, they are not parallel anymore, as they are now two-dimensional objects. And that means that the subspace of these residuals, the orthogonal complement of the diagonal, is represented by a plane through the origin that is orthogonal to the diagonal. And again, this would give us the signal plus noise representation of random variables, which we've seen before. Intuitively, the covariance of two random variables describes whether they vary in a similar fashion. And since the variation of a random variable is captured by its residual, we can compare the variation of two random variables by comparing their residuals, where I will focus on these two here. Because of that, the lengths of these lines are given by the probability-weighted norm of the residual of x and y, which I will, for the sake of a shorter notation in the following, denote by rx and ry. So what is the difference between them? It's simply the vector pointing from the end of one residual to the other, which we can represent by this purple line here, and which has a corresponding length given by the norm of the difference of the residuals. Since the norm is induced by a scalar product, abstractly this squared length is given by the squared norm of the residual of x plus the squared norm of the residual of y minus 2 times the scalar product between them. But we can also find a corresponding expression geometrically by decomposing the variation of y into a side that captures the variation of y in the direction of x and a side that captures the variation of y orthogonal to x. Then we know from the Pythagorean theorem that the squared distance between the residuals can be written as the square of the length of the residual of x plus the length of the residual of y that points into the same direction as x, plus the squared length of the part of the residual of y that is orthogonal to x. By simply expanding the first square, we see that we can use the Pythagorean theorem again just on the smaller triangle to replace the terms of the decomposition of the variation of y by the variation of y itself. So we end up with this expression here. And if we perform the same kind of analysis by decomposing the variation of x in the direction of the variation of y and the direction orthogonal to it, we find that we can also write the product of the variation of x times the variation of y in the direction of x as the product of the variation of y times the variation of x in the direction of y. So in summary, this gives us the following formula here. And the problem with this formulation is that we still need to compute the part of the variation of x in the direction of y and vice versa. Luckily, we can also find this quite easily with some geometric arguments. Since the variation of x in the direction of y and the variation of y in the direction of x are, by definition, orthogonal to their respective counterparts, we can simply calculate these lengths by using the cosinus. So if we denote the angle between one of the residuals and its part parallel to the other residual by theta, we find that this whole term simplifies to 2 times the cosinus of theta times the length of the residuals. And by rewriting the angle theta as pi minus the angle phi between the residuals, we can rewrite the term that captures the variation of x in the direction of y and vice versa as minus 2 times the cosinus of phi times the length of the residuals. While this derivation is slightly messy in terms of notation, the result is really nice for at least 4 reasons. First of all, it shows us that the scalar product of the residuals really measures the length of these residuals multiplied by the corresponding angle between them. Second, we have seen that the variation of x in the direction of y and the variation of y in the direction of x, that is, how much they vary together, namely the covariance of x and y, is simply captured by this term here, which measures how much one of these residuals can be explained in terms of the other. And based on this formula, we can see, for example, that this is a term that is symmetric in x and y, such that the covariance should be symmetric in x and y. Third, if we translate these geometric terms back to stochastic ones, we find that the variance of x minus y can be written as the variance of x plus the variance of y minus 2 times the covariance of x and y, which is basically the formula of Bienaymé from probability theory. So we again find a well-known formula by using the Pythagorean theorem in the probability-weighted geometry. And lastly, after having seen this formula for the covariance, the correlation follows trivially. If we recall the definition of correlation of x and y as covariance of x and y divided by the corresponding standard deviations, we can now plug in the formulas that we have found so far. We replace the covariance by the probability-weighted scalar product between the residuals of x and y, which in turn is simply the corresponding norms of these residuals times the cosinus of the angle between them. And similarly, the standard deviation was identified as the norm of the residual. So if we remove the terms that cancel out, we simply get that the correlation of two random variables x and y is the cosinus of the angle between their residuals in the probability-weighted geometry. And seeing this, we can also directly conclude that the possible values for the correlation are given by the range of the cosinus, which is the interval from -1 to 1. That's pretty nice, right? And now, if we look back at where we started, it is actually no wonder that the variance, the standard deviation, and the correlation are all defined in terms of the covariance, simply because they measure lengths and angles, which in the case of a Hilbert space are defined through a scalar product. The only thing we should really not forget about here is the fact that all of this holds in the probability-weighted geometry, not the standard Euclidean one. Okay, so I think this is enough for today. I hope you liked the video. For me, it was actually kind of fun, but also somehow harder to get it right. So I hope I succeeded here and you could learn something from it. And yeah, thanks for watching.